Oh, don't. Okay, we are recording. Here we go. All right, so we're learning about inverse functions today. First thing I need to do before we can actually start working on these is tell you what an inverse is, because I'm pretty sure you guys haven't done that before. It all relates to input versus output. Okay, every function, there's an input and an output, right? X is the input and Y is the output. You put some number into the function, you crunch the numbers, and you get some result when you're done. Okay, the number you put in is the input, and the number you get out when you're all done is the output. Okay, well, an inverse function basically takes that and flips it around. Okay, so definition goes something like this. An inverse of a function, and it is written as f with a little -1 of x, like that. I know, it looks like you're raising it to the negative first power, but that's actually the notation just for inverse of x. So f inverse of x is how you would write, or how you would say that, is a function where the inputs of f become the outputs, and the outputs of f become the inputs. Okay, I know it's a lot to write down, but like I said, it's pretty straightforward concept, though, as far as inputs become outputs and outputs become inputs. So I just got done saying that in general, x is what we use for input, and y is what we use for output. So if input becomes output and output becomes input in an inverse, basically all that means is x and y are going to swap. Okay? So x becomes y, and y becomes x. So when you're actually doing this stuff in practice, it's not so bad. So if I had, let's say, like an equation, y equals x squared plus 3, the inverse of that would be that same equation, but you rewrite the y's as x's and the x's as y's. Yep. The inverse of y equals x squared plus 3 is x equals y squared plus 3. All right. And then one other thing that I might ask you to do with that then is to verify, is the inverse actually a function or not? Okay. So something that's a function, does anybody remember how we test to see if something's a function from Algebra 1? No? Okay. I'll refresh your memory then. A function is an equation where every time you put in one input, there's exactly one output. Does that sound at least familiar? Yeah. Okay. One output for every one input. Okay. I can't get more than one result from plugging in one number. I only get one result from plugging in one number. Okay. So to test for that, okay, I need to take this thing then and solve it for y. Okay. I'm going to turn this thing, see if I can turn this thing into a function written that way, and then check that real quick, that idea of is there one output for every one input. So solving this equation for y, what's the first thing I need to do? All right, subtract the 3. Okay, so I have x minus 3 equals y squared. And now what? Square root both sides. But remember, if I square root both sides of an equation, what do I have to have with the square root? Plus or minus. Okay. So y equals plus or minus the square root of x minus 3. So you tell me, is this thing a function or not? No. Because if I put one number in for x, how many results am I getting? 2. I'm getting 2 outputs for every 1 input that I put into this thing. Okay? So it is not a function. Okay? Now, the inverse exists. However, the inverse is not a function, though. Okay? So if I were to try and graph this thing or something, it wouldn't pass the vertical line test and that sort of thing. So inverse is here, but it is not a function. So we'll just jot that down. Inverse, not a function. Okay, so let's try another one. Let's say we have, and this time I'm going to use a little function notation with it, but it's not really going to change the game all that much. So let's say we got f of x equals 2x minus 7. All right, and keep in mind f of x is really just a fancy way to write what? Y. Okay, so if it makes you happy, if you think it's easier, I'm totally fine. Just rewrite the equation and replace the f of x with a y, so it looks kind of like the last one we did, and just roll it from there. That's fine. But just know that in your homework, they're going to write these things with f of x instead of y. Okay? So, keeping in mind that f of x is really just y, what's the inverse of this one? Mm-hmm. All right, so looking at that, do you believe that the inverse of this one is actually a function? Yeah, it's just linear, right? So we should be able to solve for y, and there's not going to be any issue like the last one, right? There's no plus or minus that should pop up this time. So let's do that. Go ahead and take that equation, solve it for y. All right, I'll do the same thing up here. And let's see what we have. So I ended up with y equals x plus 7 all divided by 2. Right? I had to add the 7 and then divide by 2. Okay, so is that a function? Yeah. Am I getting one output for every one input? Absolutely. Every number I put in for x, that's just going to give me one number for y. Okay, so this inverse is a function. And if the inverse happens to be a function, then I can write it in that little inverse function notation stuff that I showed you at the very beginning of your notes. That little f with the -1 thing. All right, so for this one, we would say f inverse of x equals x plus 7 over 2. We can only do that if the inverse is a function because f of x is function notation, right? So this one over here, I couldn't say f inverse of x equals that because this was not a function, okay? This one was, so I can make it a little cleaner like that, okay? So that's the idea, at least as far as finding an inverse, okay? So some other stuff we're going to look at is how do the graphs relate to each other? How do we verify that we've got inverses? Stuff like that, okay? So let's go to this graphing thing. All right, so there's a relationship between a function and its inverse if you were to graph the two on the same coordinate plane together. All right, so we're going to take just a couple of these functions and their inverses and go on your calculator and take a look at the two graphed next to each other. So first ones I want to look at, let's just do these last two that we just worked on, okay? Or just this last example, but these two equations. So if you graph f of x equals 2x minus 7, and then with it f inverse x plus 7 over 2. All right, and be careful, this one, make sure the x plus 7 is in parentheses when you type it in. And then just go off to the side here, take a minute, and kind of just sketch what you see. And you might not notice the pattern just from this one, so we'll do a couple of these. But make sure you get yourself a standard window there, and then sketch what you see. It doesn't have to be anything spectacular looking, just as long as you got the basic idea of what it looks like. All right, so I got something that kind of looks like that. That look like what you guys have too. It should be a couple of lines, right? They're both linear. Okay, and they're intersecting like up over here somewhere. Okay, so like I said, that's probably not enough to really get a good idea of what's going on here. Maybe you see it, maybe not. But let's do a couple more. So I'm going to go ahead and just do the inverse work for you on this one. Okay, so if we do x to the third, the inverse of x to the third is actually the cube root of x, which may or may not come as a surprise to you. I don't know. If you work it out by hand, you can double check me on that, but that's right. It's the cube root. So if we graph those two together, type those into your calculator real quick, and let's take a look at what those two are. They look kind of like that. So given these two sets of graphs, anyone think they know what's going on here? Rotating. They're not rotated. It's a good guess, though. It is a type of transformation. They're reflections of each other. Yeah. Okay. Now, where is the line of reflection for each one of these, though? Well, it's, what do you mean by 0? Nope. It would be the line of reflection. It's not the y-axis, because think about if it was the y-axis, this one right here would then like flip around over there. And it's not the x, because then this one would go like this, right? So it's not the x or the y-axis. It's actually another line. It's a diagonal line. You guys see that? If I draw in a diagonal line into each of these, that's where they're being reflected. Okay. It does. Okay. Does that make a little bit more sense? How that's the line of reflection? If you take one and around that one, it works. Okay. This line is the line y equals x. Now think about that for a second. The line y equals x. Well, what are we doing when we take an inverse? Well, answer my other question. What are we doing when we take an inverse? We're swapping y and x, okay? So wouldn't it make sense that all the points that are on the line y equals x wouldn't change? Yeah. Because the x and the y are already the same. So if you swap them, it looks the same. So notice how any points that line up on the line here are still on the line, right, when we do the inverse graph. Same thing here. This one had 3 of them. Boom, boom, boom. Those 3, they're all still on that line. And then all the rest of them, the x's and the y's swap, so they just go around the line then. Okay? That's why that works. So if you don't even know the equation of an inverse, you can many times sketch what the graph should look like of an inverse. Okay? So that's what we're going to do next. I'm going to graph you guys a function, some kind of mystery function, we don't know its equation, and see if we can then use this idea to sketch what its inverse at least should look like. Okay? It's another way to kind of analyze inverses, even if we don't have an equation to go with it. So, all right, let's try this. Okay, so let's say we've got that's our original function. Okay, so what does its inverse look like? Well, before I try to start to do this other one, I'm going to put in here that y equals x line. I'm going to just put that little dotted line through it. So it would be something kind of like this. All right. And then the rest is just kind of eyeballing it the best that you can. And, you know, sometimes, like, I would do something like this where I just turn my paper. Sometimes that's a little easier for people. And then you can kind of see how you need to do that reflection then. Okay. So we want the other one to go something like that. So then when you have it back like that, looks something like that. So then that curve that I just drew on there, that would be our inverse. Okay, so we can get a look at what that thing is without actually knowing what the equation was to get started with. Okay. So, all right, so that's one way. Another way we can kind of investigate inverses. A third way we can do it, sometimes we don't have an equation, we don't have a graph, but we have data. We have a table of data. This is by far the easiest, okay? Again, keep in the back of your mind, what do you do to find an inverse, okay? Don't say it out loud, but just think it. All right, so let's say we got that table of values, okay? So we got this function when x is 0, 1, 2, 5, 8, and 10. We have these y values that go with them. So how do you suppose I'm going to find the inverse of that? Just flip the table, right? What do you do when you take an inverse? X becomes y and y becomes x. Okay. And I'm just going to use y here. So negative 2, 0 would be the first point. Negative 5, 1. 0, 2. 3, 5. 12, 8. And 0, 10. It is literally that easy. Okay. Follow-up question, though, for you. Is this inverse a function? Am I getting one output for every input?
No. Yes. No, because it's 0.
Okay, be careful, all right? So in this table, in your inverse, here are your list of inputs now for the inverse, right? Is there some input on here where I'm getting more than one output? Yeah, when x is 0, I get a 2, and I also get a 10, right? Well, it does count as an input, but it just doesn't count as a function then. Okay, I'm not getting just one output for every one input. 0 is one input, but I'm getting two. Wow, that's really bright. But I'm getting two outputs for that one input. So this inverse can't be a function then. Okay. Okay, so that's using tables to do it. All right. All right, so the last thing I want to show you guys, and then we can be done, is verifying inverses. Okay, so here's the idea. I'm going to write this down. It's probably not going to make a ton of sense, but then afterwards I will explain what it means. So if f of x and g of x are inverses, then f of g of x equals x, and g of f of x equals x. Okay, so that's something I think that's probably a little new to you guys. This f of g of x and this g of f of x. Okay, those are what are called compositions. And a composition is basically you take one function and you plug it into the other one. It's not just a number you're plugging in. You're plugging in an entire function into the other one. Okay? So, I'll give you an example. So, here's a function and an inverse that we came up with earlier. We're going to assume for right now that we don't know that these things are inverses just yet. Okay? And we're trying to figure out if they actually are. Okay? So we can use this little test to do that. So, f of g of x basically means take the f of x function, and in place of x, you're going to put the entire g of x function in there. So what I do is I just write out f of x, but be prepared to erase. I write out my f of x equation, and then I'm going to erase my x. And in place of x, I'm going to put this, the entire equation for g. So I got to move my minus sign over a little bit. Okay, so I've made a substitution, right? I've taken this entire thing and substituted it in here in place of where x was. And now I got to try and simplify that thing. And hopefully, if it is indeed an inverse, simplifying all of this should come out to just x. Okay, so let's try that once. What? It will, yeah. So first things first, I'm multiplying by 2, but then I'm dividing by 2. So what can I do with these 2's? Those will cancel out. So then I'm left with an x plus 7. But then, of course, I have the minus 7 on the end. So x plus 7 minus 7 is just x. So that worked, right? Got it down to x. Now I got to go the other way, too. I got to take the f function and put it in the g function, okay? So to go the other way, I'm going to start by just writing the g function with x. But again, be prepared to do a little erasing there. So it would be x plus 7 over 2. However, I'm going to replace the x with this entire equation. So I've got a 2x minus 7 going in, then plus 7 divided by 2. Okay, so 2x minus 7 plus 7. What's going to happen there first? 7's are gone. So I got 2x left over, still divided by 2, but what's 2x over 2? It's just x, right? 2 over 2 is 1, so it works. So I have verified that these two functions, 2x minus 7 and x plus 7 over 2, are inverses of each other by doing that little substitution rule. Okay? So this is attacking it from the angle of, I don't know if they're inverses or not. I'm going to quick check, and I can do the plug it in thing, and that'll tell me that they are indeed inverses. Okay. Okay. Real quick, before you guys get started on your homework, I noticed one yesterday that somebody was working on, and they were getting a little bit confused, and I wanted to just clarify something. So I'll do one quick inverse problem with you guys. And just see if this makes sense. So we're going to start with, let's say we want to find the inverse of this, okay? So our function is x squared, but only when x is greater than or equal to 0, okay? So let's think about the graph of this for just a second. What does this thing look like if it's x squared, but only when x is greater than or equal to 0? It's a parabola, but it does, well, x squared, even without this, that would be a parabola that points up, right? It's just x squared. Yep, vertex is on the origin, but what else? It's only half of it. It's only when x is greater than 0. So it would look like that. Okay? It's when x is greater than or equal to 0. Okay? So the left half of this parabola doesn't even exist. Okay? So if I'm going for the inverse, I'm going to switch my x and y. Okay? Keep this graph in mind as we work through this. Okay? So what do I do now to solve it for y? Square root both sides? Okay? But here's the thing. I don't need the plus or minus. Why not? Because it's only positive. It's only the positive half. So who needs the minus, right? Because I know it's only the positive half of this thing. So it's just the positive square root of x, and that's it. Because it's just that positive half of the thing I started with. Okay? The only reason we ever need plus or minus is because there's a positive half and a negative half to the parabola that we start with. But in this case, they've told you it's only the positive half, so I'm not going to worry about it. And so my inverse is a function, actually, this time. It is the function square root of x because I don't have the plus or minus. I got one output for every one input this time. I'm good. Okay? So when you see this little thing over here next to an equation, okay, don't ignore it. Okay? It's actually there to help you. It's giving you something where you don't need to actually worry about the whole graph. You're just having a little piece of it, okay? Sometimes it will be x greater than or equal to 0. Sometimes it might be x less than or equal to 0. So maybe you just have the left half and not the right half. So let's say for the sake of argument, it was the left half of the parabola. What would change right here? It would be the negative square root of x equals y. You guys see that? Okay. It wouldn't, because the negative actually, remember we do the plus or minus? It's not inside the root, it's outside the root. So it'd be the negative square root of x, which is totally fine. There's nothing wrong with that. So, yeah, so be careful of that. Okay, I just wanted to show you that because it was confusing a lot of people yesterday. So, all right, I'm going to stop my recording, and then you guys can start working.